If there is a signal, it'll look like that. And you're like, there's no points on that thing. He's been talking about dots. That's because I had a plotting error, which I've since fixed. And so I'll have to fiddle a little bit with some code if there's absolutely no dots apparent on the thing. And then you can see that there's some clump where I've injected a signal, and I can exactly recover it. The confidence interval software doesn't do a great job when it has nothing to find, or when the range over which it sets limits has trouble. So the fact that these guys are scattered around is just a plotting artifact that I can fix. But so the distribution of the dots is the thing that you really want to watch. The confidence intervals are things that I can easily improve with more computation time. Okay. So this is the part where you get to ask me anything you want to find out about what I think, or anything about the measurement you want to know before you find out what the answer is.
I have a probably dumb question. Your infinite plate is not actually that much bigger than the pendulum.
Yes.
What can you say about edge effects?
So basically the first explanation is if you put your face on a wall, it sure looks infinite. And then I'm looking for information in scales of 100 microns on a thing that's 75 millimeters in diameter. So the aspect ratio there is big. The other effect is that this attractor, so this is the dummy attractor that had a vacuum baking problem, is the gravitational field from it is really quite uniform. If you have a ring and you look at the gravitational field near a ring, the error is all linear to the extent that there's an error. There are higher harmonics, but they happen at much larger displacements, or if you're offset horizontally by a lot. So it's basically, I look for the deviation from linearity because I'm looking for something that turns on and it's new when I'm close and not new when I'm far. So that's the reason I fit for a linear term in addition to the science I'm actually looking for. Anything else you want to know, or you just want to find out what's in this PDF file? Okay. What am I doing? I'm not too far away. All right, so let's see what happens. And so far as I know, I have not been alone with this data ever.
This is evidenced by the difficulty with the thumb drive.
It doesn't fit into the USB thing.
That's what it means to be blind.
Yeah, let's try the other side. There we go. Probably not even work. All right. Sometimes it auto-mounts, sometimes it doesn't. I'm still figuring this computer out. I don't know. Is that gonna work? There we go. There's some stuff. So what I'm going to do is I'm going to bring up my thesis, and then we'll scroll to the relevant page, and then we'll see what I got.
So it's code automatically inserted all the answers.
Yeah.
Final result is in the thesis.
Okay. So this is actually the last. If you were to compare this commit with the other commit, you'd get the same number, I think.
Drum roll.
And so what I'm going to show you is I'll show you both the signal with the interferometer added and subtracted, and you should look at the difference. You shouldn't just take any one. That looks like a really big signal. All right, so. Yeah, it definitely sees a thing. Let's go down where I can. Where it's going to give me the chi-squares and stuff. So this is what these raw data plots look like. And so this is with the spoil signal subtracted, but there's going to be a signal there the whole time. So it's definitely seeing a signal that's really big. Oh, that's what I get. And
Just help us here.
Yes. So the interesting thing is the distribution of these points, and they're definitely not on that side of the plot. Right. So it means that there's a signal at, this is going to be roughly 10 times gravity, and length scale is somewhere between a little under 100 microns out to a millimeter. So it's well resolved in strength, but not in width.
But what are the solid lines? What are the shaded areas?
So these are the confidence intervals that I told you would be complicated if I saw something. So.
What's the solid line?
Solid lines.
Oh, the solid lines. This is Dan and Ted. So the dashed line is Dan and Ted. Let me zoom out. So, and certainly right in here, it's got some kind of confidence interval because it's collapsed onto the real data.
What are the blue points?
Oh, so these are where it's including other systematic effects. So there's also potentially one of these other systematics could be resolved. So.
But what are the points at very large distances? The blue points or whatever color that is.
Let's see, so I'll go down to where it's just a pure gravity plot, because that's easier to see. But it definitely favors a signal. And we can go look and see whether or not there's something on the opposite side, but I'm gonna guess it's still there. So this is the systematic is subtracted. This is what you get if the systematic is not subtracted, but it's gonna look the same because it's big. And then, so this is if the systematic is added. And so they look basically the same. I'll switch to the one that's
What are those blue points?
So these other colors are other injected system, or not injected, they're
way over on the right.
So over here, every color is a different systematic that I'm fitting for, because I treat each systematic effect as a Yukawa. So they can all land on different parts of the plane. So it looks like whichever effect this light blue guy is resolved. I can figure that out.
Can you give an example of what one of those systematics would be?
Yes. And let me scroll down to where these guys are.
But I don't understand it at all. Why do they stop happening at 1 centimeter? And why are they there at a meter?
So this is you can think of it as they're showing up at they're being resolved in different places, just like a Yukawa would be.
No, but I'm asking you, what in your experiment is going to look like something happening at a meter?
Oh, so this is anything that basically looks like a linear effect. Right? It's something that's almost independent of, it's looking for curvature, but it doesn't see it. So it lands anywhere along this line. The reason that this fit goes all the way out to beyond the meter is just to let the fitter go a long way, so you don't get an edge effect from imposing that the fit can't possibly run below some scale.
Earlier in the talk you had these yellow versions, and you kind of showed a green and yellow thing within the overall landscape.
Mm-hmm.
And I don't know about the rest of the people, but I'm having a impossible time taking this and imagine. Back there I could understand where you were. Yeah. Are we able to walk back to that space and see something where you're off? I would expect that now we're going to see some kind of an island out in the white space.
Mm-hmm.
According to some of these distances and so on and so forth, in a plot, in a summary plot like that.
So I'll take you back over to that summary plot in a second.
Okay.
The important lines will be this dashed line and this
those
solid
were the boundaries.
These are the benchmarks.
The other way, those were the boundaries. I got that, but now I need to sort of see it in an island, because these confidence things I think are a little, well, as you call them, difficult.
Yes. Absolutely. So. So this is this guy, and so that dashed line was this one, and this solid line is that one.
Right.
So that gives you some sense for where this lives. But the fact that
now you're going to hop on a white space and draw a little ellipse somewhere in the white part. it's still in blue.
this is the thing where I'll have to switch
Oh,
back
you
and
have a
forth.
signal in the blue, right, got it.
Or at least, it's somewhere up here, and to actually plot it, I have to plot it for you, right?
Yeah, yeah.
So we can figure that out, so you can get some sense for where it sits compared to the expected sensitivity. Right, so, this was we can look at 100 microns, and this is something like, so this is about, it was near an alpha of 10, so then I can go confirm that for you. So, these dots all land, I can't put in the middle of the screen, right? And then I'll scroll over, and so it's something like, it's right in here, right? So that's giving you a sense for about where the signal sits. So apparently this is what it looks like when you've unblinded and resolved the signal. So,
But I thought there would be more prompt.
so that depends a lot on the character of, how the attractor is moved. The signal that I showed you that was super well clumped was injected at a factor 10 bigger than this resolved signal. So you can do an even better job of characterizing its distance. When you first start to see a signal like this, it looks like a banana, and then you start, by doing other experiments, being able to lop the ends of the banana off until you get the actual thing. So
how do we go back to that slide about the dust?
And which thing do I think it is?
Yeah. The complexity of doing this lot.
That's a great question. Let's see, that was in here. If I had to pick one of these guys.
Yeah.
It's definitely not this guy, right? Because this is a thing where I'm worried about a sign and maybe a factor 2 or something in terms of the size of that guy, so that's not it. And I'd be really surprised if it's this guy, but it could be. I can't rule it out. The test for it would be to actually bias the foil up to some voltage and then look to see if this effect got bigger, which is annoying to do technically, but it can be done. It could be one of these guys. I certainly can't rule out some short-range magnetic effect. We've constrained it as best we can, but we could definitely do better. We didn't put it onto our rotating magnetic test apparatus, for example. I'd be surprised if it were this guy. If it's a dust thing, that doesn't affect whether or not there is a signal. It just affects where it lives. So that would just say that I gotten the distance wrong. But because it's a null test, I shouldn't see, if there's a thing, there's a thing. If it's resolved, it's just where it lives.
But could it move lower enough to sit on that base systematic collection design?
That would be a big piece of dust.
It'd
be 2 hertz diameter. It'd be like when I took the experiment where something should have fallen out.
So the reconstructive bit of all your nuisance parameter is about the same as the reconstructive bit of your real signal on that lambda scale.
Yes,
Does
that's
it
true.
mean anything?
That's a thing that I'm definitely gonna have to think about. So it does look like this thing is well resolved too. Right? There's almost no light blue dots on the opposite
If you
side.
zoom out a little bit more, if you look at the effective bit of on the lambda scale, all these areas have about the same bit.
Yes. Yeah, it could be that there's
systematic.
whatever that systematic is could be so big as to be pulling the whole rest of everybody. But whatever it is quite short range. So if, but
Well, I don't.
I have to figure out which color.
I don't, sorry, I meant that the effective bit in terms of on that scale, for all the colors, it's about the same. The purple,
Yes.
the dark blue, the light blue,
Yeah.
and your real signal. All these regions are very wide.
Yes.
I think we have 40 people in a group meeting about that.
Yeah.
All right.
Yep.
If there was something exotic that was not a Yukawa that you add linearly, is the comparison you're doing with these old exclusions
So if-
necessarily applicable?
So the thing that I can do, since if we want to go find out what this guy looks like, is to go look at the force law that I extract instead of the Yukawa, which doesn't include the systematic effects, because there's no easy way to make this deal with some zoom stuff. I apologize for continuing to hit no on this. I just don't know what happens when I hit yes.
You could click do not ask again.
Yeah, that's
I
true.
mean,
All right, I'll do that next time it comes up.
or if it is a new force, but it doesn't couple to mass, or there's an
let's
infinite number of things that you could
yes.
start to consider when you say, before you say this can't be right because this other experiment.
Great. Yes, I see.
But isn't the answer in a excluded zone? Am I missing
Yes.
the point?
Well, that's what
Yes,
I was
exactly.
saying, it's an
But-
excluded zone,
But-
given a particular range of theories that he's considering.
I see.
Yeah.
So there's a way to.
Well, I don't know if there is or not. They just, you know, one thing you can do is say, what's the difference between this experiment and these other experiments? Yeah.
There ought to be some pieces up here.
This is really blind.
Yeah. So what I want is just above this.
Blind now.
All right, so this ought to give some kind of a sense for the. Oh, that's so cool.
But actually, this is really stretching out in time.
So
Yeah.
this is what I get as the reconstructed force law, and I have never ever seen something that looked like that.
Whoa.
So this is almost certainly some glitch that's showed up in one set of data that's really pulling it. But I have to go
Okay.
find out what that is. And I would guess that it may well be out of a systematic test because it looks like the long stroke systematic check. If you just look at these guys, there's no obvious curvature that would be a Yukawa interaction. It's just but you know, clearly I'm gonna have to spend a while staring at this, right?
Okay. So
So
it could just be.
which part of your talk do we ignore? Are you going to publish it this way?
So I'm absolutely going to at least state that this is what I did and this is what I got. And then after that, I've told you exactly what the entire construction of the entire analysis was when I unblinded. And that can't change. You guys can trivially hold me to that.
So that's the actual data
This is the.
on the force that everything.
This is
Reconstructed force
it's basically, so I measure the derivative of the force law with because I measure the difference in torque between one position and another. So I'm measuring the sort of local derivative, and then I need to reconstruct the integral of that derivative to get the sort of, what's the shape from which that derivative came. And then that is this integral. So there's a freedom vertically, there's a plus c from the integral, and then there's definitely uncertainty from the way all that stuff comes together. And this bootstrapping was a way to get the uncertainties on that reconstruction.
So this does look kind of glitchy, that's what you're saying?
Absolutely looks glitchy,
Yeah.
which is actually kind of great, because then I can go find the guy.
Yeah, okay. Yeah.
But because seeing something like that makes me feel like I can go find a cause, and then I can say, you know, you do this thing and you get this other limit, but absolutely when I unblinded, this is what I got.
Yeah.
Like I can't run away from that fact.